Can you see everything?
Yes, we can see your slides.
Yeah, okay. Right, thank you for the introduction. It's an honor to speak here in the workshop. I'm, as introduced before, I am Yufan Yan from Seoul National University, and my talk today will be about the screening current-induced strains in REBCO insert coils. So, okay, let's move on to the presentation. Well, first, I would like to start with listing the sources of stresses and strains in superconducting coils, well, specifically here in REBCO coils. Due to the layered structure of the tape, well, here, first we have the bending stress. And then we have to wound the coil into a particular shape, which leads to the winding stress. Afterwards, to reach the desired state of superconductivity, we will need to cool the coils down to a cryogenic temperature, which causes the thermal stress due to a mismatch of the thermal expansion coefficients between different materials. Finally, we would expect a certain level of magnetic force when energizing the coils. And this part will be the focus of this study today. Of course, if we want to build a magnet that consists of several coils, then we sometimes would have other forces like the preload and everything else. Unlike most commercial LTS magnets, unlike the commercialized low temperature superconductors, the shape of the superconducting layer in the REBCO coil had an extremely high aspect ratio. So this allows for current flow across the whole cross-section of the tape. And a direct result from this is a stronger screening current effect. So from the perspective of the magnetic field, this will introduce an error field, and this will affect the overall homogeneity and temporal stability of the magnetic field. And then following the LBC magnet, which achieved a record field over 45 Tesla, this one-sided rippling plastic deformation was mostly attributed to the excessive screening current-induced stress. It is also suggested that this distribution of screening currents should be taken into account when it comes to evaluating the stress distribution in a REBCO coil. Well, following this work, it also inspired several researchers into the characterization and mechanism of the coil deformation that is caused by the screening currents, especially in the high field applications. On the left, we have studies with direct measurements of the hoop strains, which confirmed the consistency between the screening current distribution and the hoop strain distribution. Meanwhile, we also observed conductor degradations related to the screening current induced stresses. Here in the tensile side, we observed one-sided wrinkling, and in the compressive side, we sometimes can have conductor buckling. So today we will introduce our work on the subject of screening current-induced strains in REBCO coils. First, we will present a study, a proof of concept study on the deformation of a single turn coil. And then we move on with the deformation of coils wound with multiple turns. And we will introduce a modified simulation model. After that, we will try to evaluate several viable options to provide structural reinforcements, especially in pancake coils. So first is a study on the deformation of a single turn coil. So here we have the experimental setup. According to the expression of the Lorentz force, especially particularly the radial component, we used an LTS magnet to provide a high background field that is parallel to the sample coil. And then a bigger HTS coil here was placed above the sample coil in order to generate the radial field component and induce the screening current. And then 4 strain gauges were placed on the sample tape, which measured the hoop strain component. And during the experiment, we first increased the background field magnet to 10 Tesla at the magnet center. And then we defined the parameter IHTS as the applied current in this bigger HTS coil. And then we track the change of the strain distribution in the process. So with this particular experimental setup, we here have the position of the tape defined as the h-axis, and have this one as the x-axis in this picture. So here we can see the change of hoop strains with the increase of IHTS, which was defined as the applied current in the bigger coil that is above this coil sample. We can see that this can confirm the deformation of the sample coil even without any transport currents. When it comes to the distribution, the edge further away from the magnet center, which is sensor strain gauge number 4 and number 3, we have the conductors in a tensile state, while the opposite side is in a compressive state. This particular type of distribution is consistent with the distribution of screening currents. Although at this moment, in terms of the absolute numbers, the maximum hoop strain measured at, particularly at strain gauge number 4 here, is it's still less than we expected with a high index number. So then we continued this study on the coil wound with multiple turns. Here is an overview of this modified model. So here, first we have the magnetic field, which is solved by using the TA formulation, and then the displacement field by applying the magnetic force extracted from the magnetic field model. This is here called a sequential type, and then we can feed back the strain-dependent critical current and the change of the perpendicular component of the magnetic field caused by the conductor deformation. And this type is called coupled model here. And this idea here is actually very similar to the one presented by the National High Magnetic Field Laboratory. But here we will be focusing on the measurements of strains in a small coil. When it comes to geometry assumptions here, we consider 2 extreme cases where we either have frictionless contacts between turns, or we simply treat this whole thing as a block. So perfect, each of the turns will be glued together. So in this way, overall, we will have 3 major types of models to consider, which are these, which we will call the sequential discrete model, the coupled discrete model, and the block model. As for experiments, we adopted a very similar setup to the previous one. Well, there are 2 superconducting coils, one wound with 40 turns of coated conductors, and sample coil B here was wound with an extra 6 turns of stainless steel overband, and the coil were placed away from the center of the background field magnet. In this case, the axial field and the radial field component will change simultaneously. And then each coil was equipped with 8 sensors, 8 strain gauges in total, and they were placed approximately 45 degrees apart around the circle, and this is the placement of each coil in the developed view. Here is the distribution of hoop strings under a selection of magnetic fields. We have the sample coil, the data from the sample coil A on the top, and the data from sample coil B with the overbending belt on the bottom here. On the 3 lines here represents estimations from by applying the aforementioned 3 types of models respectively. We can see that the hollow dots here, which represent the sensors that is placed closer to the solder joint, lie between the block model on the bottom here and the estimation from the coupled model in the middle. But overall, we can say that the coupled model showed better agreements in general with the measured hoop strings. And then by comparing these 3 models, this figure here showed the particular case of the sample coil A, which has 40 turns of coated conductors and no overband. We can see that, the Lorentz force induced by the screening currents caused the conductors to tilt, kind of lean towards the direction of the external field. And this will in turn modify the current distribution on the right and essentially effectively delayed the field penetration process. It's also shown that this effect is much stronger on the outer side on the right, which is shown on the right, comparing to the effect on the left, which is the part that is closer to the inner radius of this winding pack. We can also demonstrate the limit of the conductor tilting by using a simple case study. Here, let's consider a 1-turn coil in an external field, which increase monotonically following this straight line over here. So the radial field and axial field will change simultaneously. By applying this model here, we can show that with a high axial field to radial field component, radial field ratio, which is the blue section here, the deformation of the tape is dominated by the conductor tilting. And in the case where the axial to radial field ratio is lower, we can see that the hoop string is dominated, the level of the hoop string is dominated by the products of the axial field and the critical current. And of course, in the middle, we will have a mixed state. Following this study, we can then try to evaluate the effectiveness of structural reinforcements, again, particularly against the screening current induced stress. First, we have the overbending belt, which is demonstrated using the sample coil B here, which was wound with an extra 6 turns of stainless steel overband. The 2 figures on the right showed the effects of the total overbending belt on the left and the thickness of the overbending tape. We can see that the maximum hoop strain, especially in the superconducting winding pack, which is the blue line here, can be reduced by expanding the overbending belt or by using a thicker tape for the overbend. Here, the 2 blocks here show the parameters used in coil sample B. Then we can also apply a bonding agent between the top of the pancake coil and the spacer. Here we used die-cast as a first trial and a stainless steel spacer in sample A-DB. Well, here it is demonstrated in the low field as shown on the figure here. In a low external field, this method can enhance the spacer to pancake bonding against the concentrated force. But unfortunately, at around the applied field of 8 to 9 Tesla, the bonding between those two parts kind of failed with the increasing external field. So to ultimately use this in applications, we will have to find further optimizations and improve the bonding method. Finally, we arrived at our conclusions and future work. Today, we presented our study on the subject of the screening current-induced strains and stresses. First, we used a study on the deformation of a single-turn coil to provide direct observation of the screening current-induced hoop strains. And then we used a study on the deformation of coils with multiple turns to complete the coil experiment in a slightly larger scale, and then validated the coupled model in small coils. And then we offered a preliminary evaluation of the effectiveness of overbanding and the edge bonding method. In the future, we would like to further our understanding of the screening current-induced strain behavior, particularly in large-scale magnets. And ultimately, we would like to propose structural designs that is reliable, especially for high-field magnets. Of course, here a special thanks to to everyone involved in this study, our collaborators from Tsinghua University, from Chinese Academy of Sciences, and the University of Houston. Here on the bottom, we have a list of related publications for reference. Okay, this is the end of my presentation, and thank you everyone for your attention.